We are back live. Um, Welcome back. I've set up something exciting. I've set up a whiteboard that I can actually write on, which is now not working. Oh, that's... It's marginally better. Um, how's everyone doing? I hope you're doing well. Kind of insane hair this morning, but then I have kind of insane hair always. Best not to worry about it. I'm going to continue playing about with Cinnamon Ostrich data. At some point today, I should probably choose a time. I was going to do midday, but I got started late. I'm going to watch some online lectures by a channel called Primer and chat about... I don't know when I expected it to be here. Which are a lovely series exploring evolution and natural selection and exponential growth and mutation in populations, and if anyone is kind of looking for a kernel from which to start understanding what's going on right now in a more mathematical and scientific sense, this is a good place to start. So we're going to do that later. First I'm just going to do some actual, work. Let me just grab notes. So I've been thinking about it over the weekend, and I'm really not sure if there's much worth looking into in too much detail here about log normals as dark matter profiles, but I'm gonna think about it a little bit more. So the basic thesis, if you're picking it up, is that I actually noticed that a lot of dark matter profiles, if you look at them rather than density as a function of radius, if you look at them as number as a function of radius, i.e. you multiply foo by r squared, then they look a lot like a log normal distribution. And a log normal distribution is a lot more physically motivated a shape than something like a NFW, like double power law. So we've got three distributions that we want to look at, have a compare, see how well they all fit. I can choose colours. We've got NFW. I'm going to go, although it'll make it a little bit hard to see, I'm going to go up a little bit in pencil size, because it'll also make the lines a bit cleaner. So NFW is rho naught a over r plus a over r squared, I think. Let me just check that to make sure. And this is the most standard used. Can't do it that way around. Dark matter profile. Rho naught r over a plus r over a squared. We have something that was suggested as a basically more accurate, better fitting version. We have Inasto, which looks like rho equals rho naught e to the minus a r to the alpha. And you know what, let's put this in another form. This isn't normally how you talk about an anaster, but I think it's actually clearer this way. E to the minus r over big R to the alpha. And then we have the one that I'm looking at, which is, let's do it purple. I'm going to call it log normal. It's not a log normal in the thing we've been writing down here, but we'll see in a sec where we get to it. So there's something stuck on my screen. Which is rho is rho naught e to the minus log r over, running out of letters, let's call it b, squared, which is equivalent to log of something minus log of a scale radius, sigma squared, all over r squared. Oh my god. Move over. Yeah, you're doing it right. I'm using a very old iPad to do this, and it's not too happy about it. So we could ask then, I'm going to try and keep track of like where I am on the page. What's the number density? What's the number at a given radius? So this is just the density. So how much is in a little 3D slice? Oh, that drawing helps on that one. Instead, turns out it's still hard to draw on an iPad. So we might be asking how much is in a little slice on the surface of a sphere. Instead we could ask how much is in the sphere as a whole. I should just point a camera at my pencil and paper, shouldn't I? Because this is not as good. So the number in the particles in here we're going to call nr. dr particles. So nr and come on iPad, you can do it. Is it just that there are too many lines on the screen? Is 4 pi rho r squared over the mass of an individual particle. And it's, for everything we're going to be doing here, particularly because I'm going to be comparing, oh, unfortunately, when I move this, this doesn't get moved. There we go. Because I'm going to be comparing to simulations where all the dark matter particles are the same mass, that's just a constant. So, let's stick all of the 4 pi rho naught over m into n naught, and we get r a squared over is this all the right units? No, just r times a. That's why. RA over 1 plus R over A all squared. And we can do the same for the Ernesto. Let's go with this guy. Same 4 pi rho r squared, it's just a different row. So this has it's got a different n naught. Let's call it m1 just to keep any confusion out of the way. And it's just e to the minus r, big R to the alpha over r squared. Ooh. And then finally, we can do the same with the. So I'm going to go through this quite like formulaically slowly because I want to make sure that we're thinking about comparing these all on equal terms. Same with the log normal, where we actually get to the nice way around of looking at the log normal. Again, just for the sake of keeping these separate, let's call it n2. No, that's not what I get. E to the minus log. Does it matter what kind of log I take? It shouldn't do. I am going to work in log, even though maybe I should be working in ln. We'll see what happens. Log r over b squared over 2 sigma squared. So now we can start asking just trying to make sure that these all are comparable with each other. So we want the total number of particles to be constant. So we want n, which is the integral of nr dr. All of these go to 0 at infinity. Is that true of n of w? I think it is. Am I wrong about that? Looks like a useful useful paper. Oh, NFW doesn't even converge. Ugh. It's a nasty distribution. Maybe none of them converge. I can write better as well. So let's get rid of that. So we'll go to a specific outer radius when we have to. Integral 0 to some big R. I know I've got big R somewhere else. I'm going to go and change it in a sec. NR dr. Right now there's a big R in the inasto. Let's replace that with C. I wonder, for those watching, if they think all this kind of slow caretaking is it's a bit over the top, and maybe it is, but I actually find just moving through these things with absolutely no rush really helps in keeping them clear, keeping them understandable. So n we also think should be constant because there's a finite number of particles. In these halos, it kind of sucks that some of these will depend on the outer radius. Some of them won't, and so in those cases we'll take the outer radius to be infinity. So n is the integral of n0 over n0 a cubed. Then the integral of r over a squared plus r squared dr, which is, and here I'm going to be a little bit lazy, oh, I guess I could do it properly. I'm not sure whether this iPad working method is working. It's just not as dexterous as I like to be. It's not exactly that clear to read. I think I'm going to go have a think about the tech and see if we can think of a better way around to do this. So sorry if you just tuned in, I'm going to disappear again. Because yeah, it's going to be no fun to watch me working in a way that really does not work. Hopefully I'll be back soon. I'll have to think about it. Possibly make some lunch. See you in a little bit. Stay happy, healthy and sane.